Hi everyone. Let us discuss Cloud Computing Unit 1. In this, we will cover FOUNDTONS and Cloud BASICS, computing paradigms, parallel, distributed, cluster grid edge, utility, computing right arrow cloud evolution, introduction to cloud computing, definition, need, history, evolution, characteristics and essential features, on-demand self-service, elasticity, scalability, measured service, multi-tenancy, cloud architecture, layers, components, front-end, back-end, middleware, cloud storage, block file object storage, distributed file systems, GFS, HDFS, deployment models, public, private, hybrid, community cloud. Why cloud computing matters, business and technical perspectives, advantages of cloud computing, disadvantages/limitations of cloud computing, companies in the cloud today, AWS, Azure, GCP, IBM, Oracle, Salesforce, etc. Overview of cloud services. Let's look at few 2-mark and 5-mark questions in Unit 1. Topic 1. 2-mark questions. Define parallel computing. What is distributed computing? Define cluster computing. What is grid computing? Define utility computing. 5-mark questions. Explain parallel computing with an example. Differentiate between distributed computing and cluster computing. Explain grid computing and give real-world applications. What is edge computing? How does it differ from cloud computing? Explain utility computing and its role in cloud computing evolution. Introduction. Computing paradigms represent the gradual evolution of how computers process information, moving from simple single-processor systems to today's advanced cloud-based solutions. In the early stages, parallel computing emerged, where multiple processors within the same machine work together to solve different parts of a problem simultaneously, reducing execution time. This idea expanded into distributed computing, where independent computers connected over a network collaborated to perform tasks, making systems more scalable and fault-tolerant. To further enhance performance and reliability, cluster computing grouped several interconnected computers in one location to function as a single powerful system. As technology advanced, grid computing extended this concept by connecting geographically dispersed and heterogeneous resources across the world to solve massive scientific and engineering problems. The growth of data-driven applications then gave rise to edge computing, which processes information closer to its source, reducing delays and enabling real-time decision-making in areas like autonomous vehicles and IoT devices. Alongside these, utility computing introduced the idea of delivering IT resources like electricity or water, where users pay only for what they consume, making computing more affordable and accessible. Finally, all these paradigms converged into cloud computing, which integrates their strengths to provide scalable, on-demand, and elastic resources accessible over the internet, powering modern applications from storage and communication to artificial intelligence and big data analytics. Parallel computing. Parallel computing is a method where a task is divided into smaller subtasks that are executed simultaneously on multiple processors within the same machine. This approach reduces the total execution time and is particularly useful for tasks that require high-performance computation. For example, weather prediction models split a geographical area into smaller regions, each processed concurrently by different processors to generate faster and more accurate forecasts. The main benefit of parallel computing is faster computation, making it suitable for scientific simulations, complex calculations, and data-intensive applications. Distributed computing. Distributed computing involves multiple independent computers connected via a network that work together to solve a problem. Each computer performs part of the task and communicates results with others, enabling collaborative processing across locations. A classic example is the SETI at Home project, which uses volunteers' computers worldwide to analyze radio signals from space. Similarly, Hadoop clusters for big data processing distribute data across several machines to process large datasets efficiently. The advantages of distributed computing include fault tolerance, resource sharing, and scalability, allowing systems to handle larger workloads than a single machine could. Cluster computing. Cluster computing consists of a group of homogeneous computers, usually in the same location, that work together as a single powerful system. The computers in a cluster are tightly connected and coordinated to improve performance and reliability. For instance, Google's search engine relies on server clusters to handle millions of search queries simultaneously, ensuring that the system remains available even if some servers fail. The benefits of cluster computing include high availability, fault tolerance, and optimized performance, making it ideal for applications requiring continuous operation and fast processing. Grid computing. Grid computing involves combining heterogeneous computing resources that are geographically distributed to work together on large-scale problems. Unlike clusters, grid systems can use computers of different types and from different locations, connected through the internet or other networks. For example, the CERN Large Hadron Collider, LHC, experiments and other global scientific collaborations use grid computing to analyze enormous volumes of data. By sharing resources across research institutions worldwide, the main advantage of grid computing is the cost-effective utilization of idle resources, allowing organizations to harness computing power without investing in dedicated infrastructure. Edge computing. Edge computing processes data close to the source where it is generated, rather than sending it to a centralized cloud. This reduces latency and enables real-time decision-making, which is critical for applications requiring immediate responses. A common example is self-driving cars, which process data from cameras and sensors locally to make split-second driving decisions. Similarly, IoT devices like smart cameras and industrial sensors use edge computing to analyze data on site. The key difference from cloud computing is that edge computing is local and real-time, whereas cloud computing is centralized and may introduce delays due to data transfer. Utility computing. Utility computing delivers IT resources such as processing power, storage, and software as a metered service, where users pay only for what they consume. This approach introduced a pay-as-you-go model for computing, similar to electricity or water usage. For instance, Amazon EC2 charges users hourly for virtual machine usage, allowing businesses to scale resources up or down based on demand. The significance of utility computing lies in its flexibility and cost-effectiveness, laying the foundation for modern commercial cloud computing services. Thank you. Please like, share, and subscribe.